Hello, everyone. Thank you for being here today, both offline and online. I really appreciate your time, and this is a moment I've been looking forward to for quite a while. And I'm super excited to talk to you today about two topics. The first one is text graph encoders, and the second one is retrieval-augmented generation. I think no one would be surprised to see this sort of user interface. It has become super popular since the release of ChatGPT at the end of 2022, where we typically have a user that has a query, and the user expects a response from a system. But behind such simple user interfaces, there are actually quite complex functionalities, such as the deep research functionality released by the major players in this field, where the system does not only have to ingest a query, but it also has to devise a plan, which implies retrieving some information, perhaps reissuing some of the queries, and finally coming back to the user with a compiled report that reflects the retrieved content, but also the user intent. So today we're going to look at a very simple example in the same user interface we've seen before. And we start with a query, which asks, which cat clashed with Larry during his time in office? And in order to solve this query, we need to first figure out who Larry is and why would a cat clash with Larry in the first place. Well, it turns out that Larry is itself a cat, and it is a special one. It holds the role of chief mouser to the cabinet office, which has been appointed by the Prime Minister of the United Kingdom. And Larry currently resides in the 10 Downing Street. So perhaps this sort of info box information, this sort of encyclopedic information is already present within the parametric knowledge of these big systems. And by parametric knowledge here, I mean the weights of these models. So they've seen lots of information during their pre-training, and now we ask them this query, and we are getting the following answer. Larry had several altercations with Sybil, a fellow cat in the cabinet office, especially over food and office space. So this looks like a very plausible answer, and in this setting of closed book scenario, where the system does not retrieve any information, it just, generates information from its parametric knowledge, I would say that this answer is fairly plausible, right? I would consider it as a fair answer, and I could believe this is actually a correct answer. Well, it turns out that this answer is not super factual, so some of this information is actually hallucinated. So we need to solve this issue because we need to build trust in the users that use these systems. So how do we get around it? Well, people have thought of moving away from closed book scenario to open book scenarios where we retrieve some information, such as the encyclopedic information from Wikipedia about Larry, indicated here as a blue node. But we might also retrieve information about other entities, for instance, the Sybil and the cabinet office that has been mentioned in the actual answer. Or we might retrieve even more information. Here is the target entity that we try to point at, which is Palmerston, which is also chief mouser, but to a different office. So one might say, hey, we currently have all the information on all the entities needed to actually solve this query. So what happens if we give this information to the model, and this sort of information is now called non-parametric, as it is not part of the parametric knowledge of the model. So you can see this as information that gets updated over time, and we retrieve it at inference time, so on the fly. And yeah, so if we combine both the parametric and the non-parametric knowledge, we might get an answer such as, Larry has served as chief mouser to the cabinet office since 2011. Other government cats include Palmerston and Gladstone. While these cats had overlapping tenures, no specific conflict is clearly identified. So while, as I told you before, our target is actually Palmerston, and while this answer is factually correct, so there's no actual hallucination happening here, unfortunately, this answer is not correct because it did not identify Palmerston. And as you can see, from the answer, it states no specific conflict is clearly identified, which means that in the text we retrieved, there is nothing explicit about their conflicts. So the thing is that, documents, we can retrieve documents, but there are also a connection between those that is at the meta level. So it is a meta level of information. And here we have a hierarchy between these documents or relations between these documents. So for instance, we have that Larry works in cabinet office. So this sort of relationship is giving us more information. For instance, we could also have an explicit relationship that goes from Palmerston to Larry with the relationship has rival. And we could also assume to have a piece of text that grounds this relationship. And for instance, we have a piece of information that is coming from the news that states Larry, the cat, treated by the vet after war with rival Palmerston at number 10. However, if we look at the query again, we see that the query is asking the reverse directionality from Larry to Palmerston. So this means that we need to do some sort of an inference. So we need to do some sort of a link prediction between Larry and Palmerston with the same relationship as rival. So now that we have this text attributed graph, so it's a graph where the nodes and relations have a textual description, and given the current query, we can give this as an input to the model. So now we moved from non-parametric to structured non-parametric knowledge. And if we look at the answer and we look at the end of it, it says the two were known for their frequent turf disputes and confrontations outside number 10. So we can clearly see that this answer is correct. And this is because now the information is explicit, but it stands in another level that is not only the textual one, it's also in the structured information. So we've seen that there are multiple interacting components. We've seen the difference between parametric and non-parametric knowledge, also the structured non-parametric knowledge. We've seen that we're dealing with both text and graph information, so unstructured and structured information. We've seen that we need to retrieve this sort of information and perhaps do some link prediction. So we need to complete the graph. And finally, as I said before, because we're interacting with users, we want to make sure that the response reflects the retrieved content and the user intent. So we need to align these responses. So there are lots of things going on here, but today, as an outline, I would like to focus on three main components. The first one is we're going to look at these retrieval pipelines and some of their limitations. In the second part, we're going to look at how to encode both text and graph information into the same model. And finally, we're going to look at the problem on how to build systems that align other systems with respect to the retrieved content and the user intent. So in the first part, we're going to look at the RAG, so from chapter 3. And then we're going to look at the paper titled Refine, Retrieval, Re-ranker, Reader Fine-Tuning. Then we're going to move on into the second part, where we're going to look at chapter 6 about self-attention and structural encoding. Then we're going to look at chapter 8, where we're going to present the paper Fast and Frugal Text Graph Models. And finally, we're going to look at chapter 5, where we're going to present the paper RAG-Referee, Referee for RAG, where we are trying to build contextual reward models for a RAG. So these are the three main parts that I would like to touch today, and let's focus on the first one. So as I said, we're going to look a bit at RAG and the higher level, and we start with our simple user interface and the query we had at the beginning. And we now look at the retrieval-augmented generation pipeline, which takes as input the query and encodes it. So it's the textual information of the query that gets encoded into a single vector. Then we have our contexts, which can be both structured and unstructured, that are also encoded into a single vector. And then we perform a search, a vector search. We're given a query, and these contexts that have been embedded, we're going to retrieve the top K most relevant ones. And then we're going to give it to our augmentation phase, which consists of a prompt that the user has defined and the query of the current user, and we're going to augment this prompt with the context that has been retrieved. And finally, we're going to give this to the reader, i.e. a generator. In this case, it's an LLM that actually produces the response. So as you can see, there are some few components, and this again covers a bit of chapter 3. And now we're going to dive into chapter 4, where we take a look at the specific parts of this pipeline. And in the first part, we're going to focus on the query encoder, the retrieve, and the generate components of this system. And the research question we're trying to address today is, we've seen that these retrieval-based conversational question answering pipelines have some limitations, and we wanted to address those. And we do this in our findings of EMNLP 2023 paper titled Strong and Efficient Baselines for Open Domain Conversational Question Answering. So we're going to look first at the retriever, and this is implemented with the already known and existing architecture called dense passage retrieval, which takes as input a conversation history and a set of passages. It encodes both the conversation and the passages in parallel and independently. And then it performs a dot product search in order to retrieve the top K most relevant passages for the current conversation history. So given this pre-existing architecture, one of our contributions is to identify some limitations. The first one is the reduced coverage of the retriever. What does it mean? Well, if we assume we have a gold passage that contains the answer, the question we're asking is the gold passage present in the top K passages we're retrieving? If it's not, then it means that you're not doing good retrieval. Second is the lack of cross-semantic encoding between the conversation and the retrieved passages from this retriever component. What does it mean? Well, as I said before, the conversation encoder and the passage encoder encode information independently, so there is no interaction during encoding between the conversation and the passages. They cannot pay attention to each other, and the passages cannot pay attention to each other during encoding either. So in order to solve these issues, we introduced a re-ranker component. We're not the first ones to think about a re-ranker, but I think we're the first ones to think of re-ranking working at an induced representation level. What does it mean induced? It means that we work at embedding level. So here, the semantic re-ranker is implemented as a transformer, where it takes as input the vector representations of the conversation and the passages, and self-attention will basically let the conversation and the passages look at each other and exchange information to finally create new representations that are perhaps better and lead to better ranking. So in order to see if the semantic re-ranker actually works, we first we're going to look at the Topioca dataset, which is a very interesting question answering dataset that has this feature where the topic of the current conversation changes. So as you can see here, we have the topic shifting during the conversation. And then we have a more classical dataset or QAC, so it's open domain question answering dataset, where you have a series of question answering, and then you do a retrieval up at some point, and then you retrieve the information, and then you give it to the system to produce an answer. So we're going to look at the top K retrieval, and we're going to measure the accuracy of figuring out if the gold passage has been fished and if the gold passage is present in the top K. And the baseline is without semantic re-ranker, so we just do a normal retrieval. And the second one is after adding our semantic re-ranker and performing some fine-tuning on the conversation encoder. So we are only fine-tuning that part, and we leave the passage encoder fixed, as is the one that is more computationally expensive, since we need to encode all our context there. Okay, so if you look at top 1, we can already see that without the semantic re-ranker, the performance is not great. but with the semantic re-ranker, we can gain from 18 to 27 points depending on the data set. So there is a huge boost with the semantic re-ranker in top 1. Of course, increasing the top K increases the likelihood of finding the gold passage in the top K we retrieved. So as you can see, the performance generally increases, and we could also increase further to 500 or 1,000 up until we get some diminishing returns. But the point I would like you to focus today is that with the semantic re-ranker, we can surface more relevant passages at a much lower top K. So here in Tapioca, we can see that we can get in top 10 the same performance as if we were to be in top 50, while in OR-Quack, we can reduce from the performance from top 500 to top 10. So we have a 50 times top K reduction, which is significant. And we are going to see that this is a desired thing that we would like to have in our model, i.e. to have the least amount of passages in input. So this is the contribution of the semantic re-ranker in combination with the pre-existing dense passage retrieval. And now we're going to see how the semantic re-ranker helps the reader, the generator, which in this case is based on the pre-existing architecture called Fusion Encoder, which is based on a T5 model. So it's an encoder-decoder architecture, and it takes as input the textual representation of the passages. It concatenates this textual representation with the conversation history, and it gives these passages conversation history pairs to the encoder, and it encodes each pair independently. So now each encoder has its own dense representations, and this architecture fuses these dense representations. And by fusing here, it means we concatenate these dense representations, and we finally fit it to the decoder, which cross-attends to these representations to finally generate the answer. So similarly as done for the dense passage retriever, we're going to also show some limitations that we identified, and this is also one of our contributions here. We identified the first limitation, which says that the reader is susceptible to noisy input. What does it mean? Well, assuming you have a gold passage that you can read from, if you have, I don't know, from 50 to 500 or 1,000 passages, it's going to be super difficult, for instance, for me, to figure out where the gold passage is actually positioned in these 1,000 passages. So similarly, also the system will have quite some trouble in distributing the attention or having a very peaky attention to the golden passage that we want to read from. The second limitation is the fact that with an increasing number of passages, the latency of the reader is going to increase significantly. So ideally, we would like to have the least amount of passages in input to the reader for it to be fast. Since we are aiming to deploy these systems to users, and potentially we want to scale to many, many users. So in order to see what does it mean to have the golden passage, or how many passages we need in input, we're going to look at Tapioca again. We look at the top K performance here, where we say we keep only the top 10 or the top 50 passages. And here we have a column that states with gold, which means that we guarantee the gold passage to be within the top K. And without gold is that the passage may or may not be within the top K. So we just have the normal likelihood of being there in the top K. Then we're going to measure the performance of the reader by looking at the exact match between the generated and the gold response, and also at F1, which measures the word overlap between the generated and the gold response. So this second metric is a bit more flexible. So if you look at the top one with gold, this gives us the upper limit, the upper bound limit of the performance of the system. So you cannot do better than this with the current system we're looking at. So the numbers do not go up to 100 here, just for you to have a bit of a context on the performance of the system. And of course, if we do not guarantee of the gold passage to be there, the performance is going to drop because the likelihood of having always the gold passage in top one, of course, it's lower than the one where we force it. So another thing I would like you to look at is when we are in the without gold case, if we increase the top K, what it means it means that we are increasing the likelihood of having the gold passage within top K, so the performance increases. So the message here is bigger top K, better performance. However, if we look at the one where we guarantee the gold passage to be present in the top K, here we see an interesting effect where the bigger top K actually leads to worse performance. So this goes into the first limitation where I said that the reader is susceptible to noisy input. So ideally, the take-home message here is that we would like to have the least amount of passages as possible with the gold passage, of course, present in this top K. And when we look at the latency of this system, as I said before, there is also a limitation. So here on the x-axis, we have the top K number of passages, and on the y-axis here we have the F1 of the baseline system. And as you can see, the bigger the K, the better the performance. However, if you look at latency, the lower the K, the better is the latency. So we can have quite a big reduction. For instance, if we focus on reducing by 5-fold from top 50 to top 10, then we're going to see a bit of a drop in performance on the baseline system. But we're going to gain a lot of latency here. So it means that we can actually reduce latency by 60%. So what we want to show here is that if we add the semantic re-ranker, we can actually obtain do not lose performance in terms of F1, but we also but we keep the 60% drop in latency. And the same goes for OR quack. And finally, we can look at the results where we include the semantic re-ranker between the DPR retriever and the FID reader. And we have different models that we're going to look at. The baseline model we're going to look at is this, the best performing one as a baseline, where we have the dense retriever, so the DPR retriever, and the generator based on FID, so the reader. We also have other baselines based on sparse retrievers, such as BM25, or DPR reader here, which means we extract the answer. So we put a boundary within the text, and we choose that as our answer. So as we will see during this presentation, we always strive to reproduce the baselines to make sure that our numbers that we propose can be put in context with the baselines. So as you can see here, we managed to reproduce the baseline. Finally, we add our retrieval re-ranker reader approach, and we only keep the top 10 as a top K. And as you can see, the performance increases. For OR quack, we have a similar baseline where we try to reproduce it, and then we add the refine on top of it. And as you can see, we also obtain better results also in this dataset. So as summary of this first part, we identified the following limitations within the retriever reader sort of pipelines. The first one is the reduced coverage of the retriever. We've seen that it is not guaranteed of the top of the gold passage to be in the top K. And then we've seen that the retriever has this lack of cross-semantic encoding between the conversation and the retrieved passages. And we've seen that the semantic re-ranker solves this by adding a transformer layer that cross-attends between these two components. Then we've seen that the reader is susceptible to noisy input. So we want to reduce the number of top K, but also have the gold passage, which again is the job of the semantic re-ranker. And finally, because we are reducing the top K, we are going to also impact heavily the latency, so we're going to reduce it considerably. So what we did, we included this semantic re-ranker component and performed some targeted fine-tuning steps, both at the retriever and the reader. And we reduced the latency by 60% and outperformed the existing baseline approaches. Good. So going back to our Larry and Palmerston example, what we did is assume that we have a better retriever substantially. So it means that, This piece of information that was at a higher level with respect to the base text that we retrieved potentially now can be included into the base text that we retrieved. So ideally, we do not need to encode any other graph because we are able to retrieve this piece of information right away. Good. So this concludes the first part. We're going to move into the second one. We're going to look at how to encode both text and graph information. This means that we're going to move on from the query encoder, the retriever, and the generator to these three components. We're going to focus on the query encoder, the context encoder, and the context themselves. And the research question we're trying to address is how can we make use of both textual and structural information? And we're going to operate in a knowledge graph. And again, we are in the same inductive setting. So it's a function of a text. We're working on the embedding level. And there are some relevant publications to this research question. The first one is Transformers as Graph-to-Graph Models, presented at the Big Picture Workshop at the EMNLP 2023. This is a very nice paper because it is sort of a collection of papers that employ the graph transformer that I'm going to explain that has been part of our group for quite a while. And the paper we're actually going to focus today is the fast and frugal text graph transformers that are effective link predictors, and that has been presented at ACL 2025 in findings. Okay, so as I said before, I don't think I will surprise anyone if I show this sort of architecture. This is the transformer architecture. We're not going to look at in details at it. We're going to only focus to the multi-head attention here today. So as I said before, we are going to look at induced representations. So here we have the entities in our graph, and we are assuming that we have a way to map their textual representation to a vector. And because the transformer is a sequence-to-sequence model, we have now a sequence of entities. And the way transformer works, it first encodes these vectors into the query space, and the same set of vectors are mapped to the key space, and then there is a query key interaction between these components. So if we go back into the graph view, so we have a set of entities, a set of nodes. We have that the Palmerston can be seen as a head, Larry can be seen as a tail, and the dot product between those two elements is a relation. So in the head relation tail language, we can assume that the query extracts the head representation, the key extracts the tail representation, and the dot product represents, again, a latent relationship between a head and a tail. And another thing, it means that if every single entity or every single node needs to pay attention to every single other node, what the self-attention is creating is a fully connected graph. So what I want again to emphasize here is that self-attention corresponds to sort of a graph processing where we are extracting graph knowledge from these vectors with the queries and keys, and their interaction represents a relationship. So one of our contributions is this knowledge is contained into the vectors. So again, they're a function of a text. However, we have some information that stays outside of the text that is explicit and we want to encode, such as the Palmerston has rival Larry relationship. So how do we do that? Well, what we do is basically adding a bias to this self-attention scores and this is one of our contributions, where we basically say, hey, Palmerston and Larry, when you pay attention to each other, please be careful that there is also a bias that encodes the relationship has rival. So now all of a sudden, the transformer has encoded a graph, and because it outputs a set of vectors, it means that we can also predict the graph at the end, which is a relationship between every vector here. So potentially, because we encoded Palmerston has rival Larry, when we get at the end of the model, we can also predict Larry has rival Palmerston, and we want to solve the is Palmerston a rival of Larry question, right? So we want to backprop that sort of information. Good. So as I said before, we're working on text attributed graph. We have a set of entities, a set of nodes, and a set of relations between these nodes. And every single component in this graph has a textual information. So I'm going to represent it just compactly like this. Again, remember the head is Palmerston, the relationship has rival, and the tail is Larry. And each of those have a textual representation. And since I mentioned before that we work on induced representations, this means that we have a way to map text to vectors. And this is done by typically is a text transformer encoder or a BERT model, for instance. And in the link prediction literature, typically relations are coming from a fixed vocabulary, but we try to make them as a function of their text, since we didn't want to be bounded by this limited amount of relations, because if you get the new relation after you update the knowledge graph, now all of a sudden you would need to retrain your model in order to be aware of the new relation. But if it is a function of a text, then you just need to use the same text encoder to map it to a vector. And people have tried to make this work with some limited success, but here we are going to show you today that this can be done. And as I said before, we have that all the text elements have been encoded with this text transformer, but all these elements have been encoded independently of each other. So they do not know about their relationship. So how do we encode that? How do you encode this structure information that we have access to? So we're going to employ the thing I mentioned before, which is the graph transform encoder, which is based on the information I gave you about how to use self-attention for structure encoding, and I'm going to present it to you in detail in the next slide. So now what the graph transformer does, it takes as input this subgraph, this ego graph, where there is one center node and one hop neighborhood, and is going to put the information into this center node, the information about the neighbors and the relationship with the center node within one single vector. And this is one of our contributions. Finally, in order to learn something, you need to have a loss, and here it's called the link prediction objective, and this is implemented in a very simple way. If you remember the analogy, the classic analogy of NLP that says king minus men plus women equals queen, this imposes sort of a geometric property of the embedding space. And here we have a similar approach where we have that head plus relation needs to land into the tail representation. So Palmerston plus has rival needs to land in the vector Larry. So while this is a very simple linear translation, because everything before it is nonlinear, we can assume that this is not going to be a big problem. And also the goal of us is to show that the graph transformer is actually adding value on top of the text transformer alone. So how does the graph transformer work? Well, as I said, we have a set of vectors that have been induced from their textual representations. What we add on top is sort of a segment embedding in order to tell the model that we are encoding an ego graph. So we have a center node we're interested in and some neighboring nodes. So this will tell self-attention where to put information. And it could already do this, and you're going to see that you can obtain very good results with just this simple model. We have also ablations that you can check in the paper. However, as I said before, we wanted to encode the explicit relations between these vectors, such as we have that Palmerston has friend Gladstone. So what we do, we add a bias term in between the queries and the keys, where we map the relation text into the relation space, and then we bias the dot product between the queries and keys at every single dimension of this vector. So you'll only get a score, a high score of agreement between Palmerston and Gladstone only if they both agree on the relationship, i.e. has friend. Then we have the normal feed-forward layer, and finally we get our sequence in output. So sequence in, sequence out. So all the information is now in this Palmerston layer that we're going to use as a vector representation in order to do the link prediction objective. Good. So let's look at some results. But in order to do this, we first need to look at the metric. Here we are talking about the mean reciprocal rank metric, which implies given a query, Palmerston has rival, you need to give an answer, which is our target, Larry. And given the query, Larry has rival, you need to give the answer Palmerston. So that's what the reciprocal stands for. So the rank, it means that you need to rank in top 1, top 3, top 10, whatever top K you're interested in, and you take the average of this rank. Then we're going to look at two knowledge graphs. The first one is WordNet, which it's fairly simple. You can have things like hot is an antonym of cold, and vice versa. And a bit more complex knowledge graph is the Freebase one, where we have this example where you have James Ivory is the director of the film A Room with a View, and vice versa. So we're going to look at different models. The first model we're going to look at is BERT for link prediction, which uses a BERT model in order to do the induced representation, and then it applies the link prediction objective. And as I said before, we always strive to reproduce the baselines. As you can see here, we get very close performance to the reported ones in the same similar settings and hyperparameters. And what we did is we added some improvements over this in order to show some benefits. One of those is induced relations. So we now, instead of having fixed relations, we have them as a function of text. And as you can see in WordNet, there is not too much of an improvement, while in Freebase there is a more significant one. This is because WordNet has very short descriptions of relations, so it's typically one word, while in Freebase we have a bit more of verbose descriptions. Then, because we are working in contrastive learning, usually we define n amount of negatives. Here we decided to tie the number of negatives to the batch size. And as you can see here, basically it means that we are increasing the number of negatives and the performance goes up. And this is known for when you have a bigger number of negatives, the better the performance of your model. Then we also increase the embedding size, which again provides us with the better performance. And then we also increase the batch size. And we had a better sampling method where in the query where we have Palmerston has rival, we also keep Palmerston as a negative because we've seen that the model tends to predict the head itself. And finally, we reach from this BERT for link prediction that we reproduced to our fast and frugal text model. I will tell you what it means, fast and frugal, in a second. But what I want to emphasize here is that given a fixed GPU budget, one could only apply these incremental additions and, call it a day. And perhaps, say, hey, look, I added this new complex architecture on top and I get better results, but it's only because of using just the base model and you have a bigger budget, and i.e. you have a bigger negative batch of negatives or bigger embeddings, and you can get better performance. So we need to be super careful when we look at our baselines. So that's why we are not going to use BLP as our baseline, but we're going to use our fast and frugal model as our text-only baseline. So now we're going to look at a full table, again, WordNet and Freebase. We have also 3 new metrics. This is hits at K, which means how good you are at putting the gold passage in the first position or within the 3rd position or within the 10th position. And as I said before, we keep in the text-only models our fast and frugal model. And then we're going to compare it with structured informed models. So now we have both the text and graph model. And as you can see here, the performance increased significantly. However, we wanted to figure out if it's indeed the graph that is, adding information here. So what we try to do also, besides comparing with the previous baseline where we have substituted the graph transformer with a message passing neural net, which is, for instance, like a graph convolution network, which is this static method. And as you can see, the graph transformer is doing much better. As I said before, we wanted to figure out if the text, how important is the text part in this encoding? And what we try to do is to reduce the text encoder size from BERT base to BERT tiny, which corresponds to a 96% of reduction in terms of parameters. And if you can look at the drop, in the text-only models between the BERT-based and BERT-tiny, you can see a huge drop in performance. However, in the structure-informed models, you can only see a marginal drop. Okay, there is still a considerable drop here, like 10 points, but still the difference, the delta is not as much. Which means that the graph component is very important in this sort of learning, which is sort of, expected. And another thing I wanted to show you is that with the BERT tiny model, we can actually obtain the same performance as the BERT base from static. So this is significant because, again, we can reduce by 96% the number of parameters and still obtain way better results than a baseline model that uses BERT base. Good. We obtain very similar results also in Wikidata, which is another data set, and has also a different setting and a different evaluation. But again, text graph transformer works in all these three data sets. Another thing I want to show you is, as I said, we look at the performance relative to base models. So here on the x-axis, we have the reduction in terms of parameters with different models. So we go from tiny to base. And the y-axis, we look at some performance relative to the base model. So the first one is the MRR, so mean reciprocal rank. As you can see, if we can reduce by 90% the number of parameters, we can actually have minimal performance loss. But if you look at latency and we again reduce by 90% the number of parameters, we can have a considerable latency reduction. So as summary of our contributions in this second part, we've seen how to leverage the intrinsic graph processing capabilities of the transformer. And we showed that these fast and frugal models are both fast and frugal. So fast because we can train a very small, tiny model, and frugal because it is a very small model. So both in computation, like for training, the GPU that memory that you're going to occupy, and the inference speed is going to get influenced massively by the reduction of the text encoder, which is the one that occupies most of the computation in this encoding. And finally, we extended the inductive knowledge graph learning to a fully inductive setting where the relations are not fixed from a vocabulary, but they are also a function of the text. Within the paper, we also shown a case where we have a fully out of distribution sort of test where we give to the model relations that it has never seen during training or entities that it has not seen during training. And there are some interesting results going on there as well. So going back into our Larry and Palmerston example, well, at this point, what we did is to focus on this text attributed graphs on how to encode it. And you can now assume that you can retrieve not only pieces of text, but also graphs. So this completes the second part. And then we're going to move to the last one, which tries to build models that align other models with respect to the retrieved content and the user intent. So we're going to move from these three components to these three components. So we have a query response preference pairs and those that generated the response. So we have a generator in the augment component. So why should you even care about this? Well, as I said before, people interface with models and try to build trust into those. Models also must align to diverse goals, which means that if we want those to be safe, they need to be aligned with whatever humans consider as safe. And we've seen that reinforcement learning from human feedback or reinforcement learning from AI feedback are quite promising, but they also rely on so-called reward models, i.e., in order to align an LLM, you ask a reward model that if whatever the LLM has generated is good or bad. So you need some sort of preference pairs. You can have human annotators to do this. However, this has a problem of not being super scalable, which means that we need to build systems that are proxy for humans. So that's why we call this reward models, is inverse reinforcement learning here. However, if we build these reward models, we need to make sure that they are actually good proxies, so we need to evaluate the evaluators. So there are many, many things going on in here. And indeed, one of the research questions that we're trying to focus on is, are those reward models actually good in the RAG setting? And if not, how can they be extended? And the paper that we published at the main conference of MNLP 2025, titled RAGFERI, a referee for RAG, which concerns on building contextual reward models for retrieval-augmented generation. And we're going to dive into it now. But what is a reward model? Here I'm going to present a very simple example. So we have a XY pair, where X is a prompt that contains a query and a query and perhaps instructions, and Y is the answer. So we have, a query answer pair, and one of those answers is the chosen one, and the second one is the rejected one. And we pass this to a reward model, which can be instantiated as a LLM as a judge, which then provides a score, and we expect this score to be of the chosen answer to be bigger than the rejected answer given the current prompt. And this is called the discriminative reward model. Instead of being a generative one that tries to provide the justification, here it provides a score. So as I said before, we are extending these reward models to the RAG setting, which means that we are interested in evaluating these reward models with specific dimensions of RAG. One of those is refusal. So a reward model must choose the answer that refuses to actually provide a response. One example is, for instance, if you don't have enough information in a retrieve context, you should say, hey, I don't have enough information, I cannot answer. And that's the answer that the reward model should prefer over one that actually tries to answer. The non-refusal one is the case where these models have been gone through lots of guardrails, and sometimes they do not want to answer. And here in the non-refusal, we want to make sure that a reward model gives a higher score to a model that actually answers over the one that does not answer. Then we have dimensions such as faithfulness with respect to the retrieved content, completeness with respect to the user intent, and conciseness. For instance, you don't want to copy-paste the whole piece of text, but you want to favor conciseness. And finally, we have the overall accuracy, which puts all these dimensions into a single number. Good. Now let's look at some of the models. We here plot the OpenAI O1 performance. And as you can see, it does quite bad in the refusal and the conciseness dimensions. And if we plot an actual reward model that has been trained on 80,000 preference pairs, and it has 27 billion parameters, you can see that it has very similar struggles, which involve the refusal and the conciseness dimensions. Then we could include even bigger models like the Salesforce Judge, which has been trained with 680,000 preference pairs. And it is an even bigger model, so it's 70 billion. And again, overall, it does even worse than the other two. Again, we're evaluating these models in the RAG setting, not in the generic setting they've been training on. But this is to show that if we assume that these reward models are good at everything, this shows that they are not. In the RAG setting, they're going to fail drastically. And finally, if we plot our RAG-free model, which has been trained on only 4,000 samples, preference pairs, and it has 24 billion parameters, we can see that we obtain overall very good performance. So what is the reason of these pre-existing reward models, and why do they struggle so much? Well, they're not well suited for RAG. Why? Because the preference pairs that they receive, they, for instance, always assume to have an answer, and simply the refusal dimension signal is not present there. They've never seen answers that, models that refuse the answer. So you can't do well in this refusal dimension that we see they struggle in. So it means that they lack some RAG-specific signals, which means that we are missing reward models that are actually good for RAG. And the reason we are missing those models is because we are missing preference datasets for RAG reward models. So today we're going to focus on these two missing pieces here. So how do we build a dataset that we use to train reward models? So what we do, again, we are in a conversational question answering setting. Here we base ourselves on MS Marco. So we're trying to repurpose this dataset, which contains a set of documents, queries, and answers into preference pairs. So we're taking an old dataset and we want to, requalify it in this new era of reward models that we need. So these queries are actually produced by humans that interact with Bing, and we have a set of answers and a set of documents where the answers come from. So initially, we do a very simple filtering, make sure that a query has an answer or a query has a set of documents that we can rely on. If we don't, we just filter them out. Secondly, what we do, we employ an LLM in the middle, where we use it in order to perform some regeneration and some classification. By regeneration here, I mean that, for instance, as you see here, we have the well-informed query box, which means that we take a query and we ask the model to rewrite it in such a way that perhaps it avoids some of the spelling mistakes. So we want to make it into a state that is good for classification. And then we use the same LLM to classify the query in different categories, such as popularity, so how popular this query is, the domain of the query, if it's expected to be a complex query, or recency, so is this a time-sensitive one, or if it's even a valid one. If you ask, for instance, how many steps does it take me to get to the moon, this is not a valid question. Then we apply the stratified sampling because we want to make sure that at the end of our dataset, we are looking at all these characteristics without favoring specific ones, because we're going to have a skewed distribution here. And then after doing a big reduction in the samples with stratified sampling, then we employ Apache 2 and MIT models. And I want to emphasize the reason we're doing this is because if we're going to create a dataset used to train other models, we want to make sure that we don't bring over any license limitation. So that's why we only use Apache 2 and MIT models. So given documents and the word form queries, we ask these set of models to generate an answer. And then we're going to use the same LLM in the middle to judge if the model has deflected correctly, or if the answer is eligible with respect to the goal answer, or if the answer contains actual facts that come from the documents themselves. And finally, we do some more sampling and we apply some heuristics in order to choose the chosen and rejected pair. One simple heuristic is, for instance, in the deflection case, you just check if the model has correctly deflected when there was not enough information there to start with. And if it did not deflect, then it goes into the rejected bucket. And here we do more sampling by what I mean that besides balancing the query characteristics that we've seen before, we also balance the models that have responded. We don't want to favor any a specific type of model because we have reasoning and non-reasoning models, or they have a specific style of answering. We want to make sure that everything is as balanced as possible and it covers as much as possible, but still retaining a very small data set. Good. So to look at an example about stratified sampling, we take a dimension, which is the recency, so the time-sensitive one. We have like evergreen questions that people always ask. Then we have some fast-changing one in the green here, and slow-changing ones in red. So as you can see, we start with the first 500 million queries, and then we do a first down sampling, and we have a 10 times reduction. As you can see, we already managed to like unskew it a bit. Still, the evergreen questions are predominant because that's part of the distribution. But then if we further subsample based on the models, and again, all the categories, then we managed to increase a bit more also the other dimensions. It's still a bit skewed. This is not perfect, but since there are multiple interacting components, I think this is already a big plus, where we have a 10 reduction in the first side and another 10 in the second part. So we have a total of 100 x reduction. So we go from 500,000 to 5,000 examples. So how many preference pairs do we actually need? So here I'm going to plot on x-axis the number of preference pairs and the overall accuracy. And I'm going to plot the baseline models. So we have the ones that have not been trained with RAG, right? Like there's something that we're assuming they're good at RAG. And what I want to show you here is that they're actually indeed not suitable for this because they all fall into this, coin toss sort of performance. So it's chance level performance. So half of the time they will do well, half of the time they will do bad. So they are not really useful models, right? And then we are plotting here the curve where in the black we have the average value where we trained 4 models between 7 billion to 24 billion between 2 families of models. And here you see their variance in performance. But as you can see, already with 1,000 examples, you can do much better than the baseline models, up to 4,000, where you reach the peak performance, and this define our model based on Mistral small and fine-tune with RAG-free. And after that, you kind of plateau. What I want to show you is that our dataset actually encodes RAG-specific signals, because if we train our models only on the query answer output without the documents, then so without grounding, then our performance also goes into the chance level, which is in line with the previous model. So it does show that the previous models do struggle because of this not being grounded, or do not know how to ground themselves into the documents. And yeah, I think this is a very interesting finding. Good. So summary of our contributions in this part, we have that we identified several limitations of current reward models, and we introduced a methodology for constructing this preference dataset that are specific for RAG. And we are releasing license-friendly models and datasets. So everything here is either Apache 2 or MIT. Good. So going back to our Larry and Palmerston example, what we try to do here is, to align the response with respect to the retrieved content. Great. So let's wrap up with the thesis contribution. Of course, we didn't cover all the chapters. There are many other ones. There is another one about graph encoding we did not cover today. I had to select one of the 2. But we look at the retrieval-based pipelines and their limitations, right? We look at the DPR and the FID and the way how the semantic re-ranker increases the performance of both components. We looked at how to encode both in graph information. Here is in the graph transformer, right? Like works on both text and graph information. And how to align responses with regard to the retrieved content and the user intent. And here we employed the RAG-free strategy, and where we fine-tune models after creating a data set. So these are the 3 main things we've seen today. And I would also like to say that in my view, what we do in this thesis, we sort of lay the foundation. So this is only the start of this endeavor for future LLMs that are being used as information seeking systems, and they are capable of integrating both structured and unstructured information within a unified attention-based framework. So we use attention as a unified framework. So going back into our Larry and Palmerston example, well, at this stage we have all the components necessary to solve this example. So as you see, it's a very simple example, but somehow it's super complex to solve it, right? It implies lots of moving components and lots of strategies. So looking forward, what I think where things are going is we're going to see this next-gen retrieval-augmented generation, which include a graph-driven retrieval. So we do not only retrieve text, we actually retrieve graphs. I think people are already doing this. The issue is how do you actually read the graph information? Do you use cross-attention to read from these vectors? Do you just read from the retrieve vector? There are many questions here that need to be answered. And as we've seen, we only have two modalities here, the text and the graph. And we have this unified attention framework, but potentially with these omni models, which encode any modality and output any modality. So we have audio, text, video, potentially graph now, and so on. Ideally, we would like to have this in a unified attention framework. And if there is any structure between these modalities that we want to capture, we can use the graph transformer that we proposed here. And finally, here we looked at specifically conversational question answering data sets. But I think we're going to go forward to truly general purpose information seeking systems. So systems that do seek information that is useful for the user. For instance, if you do scientific research and you need to be encoding lots of modalities, and you need to do lots of things like similar to the deep research that I mentioned at the beginning of this presentation. So this brings me to the end of my presentation today, and I hope you have questions.